हेलो दोस्तों, आज हम आपको समझाएंगे सेमीकंडक्टर्स के बारे में।
तो वीडियो शुरू करते हैं। Semiconductors are the building blocks of modern electronics. These devices are electronic components, much like resistors, capacitors, transformers and relays, except that they exploit the electron behavior of semiconductor materials. Since the late 1950s, semiconductor devices have replaced thermionic devices, that is, vacuum tubes, in most applications. They use electronic conduction in the solid state, as opposed to the gaseous state such as occurs during thermionic emission in a high vacuum. As such, semiconductors are often referred to as solid-state devices. Characteristics and properties. The key characteristics that have allowed solid-state devices to replace vacuum tubes in most applications are their small size and weight, low operating voltages, lower power dissipation, higher reliability and extremely long life. In addition, there is no warm-up period required since semiconductors are absent the cathode heater. However, semiconductors typically do not perform as well as vacuum tubes for high power, high frequency operation, such as television broadcasting, and they are much more vulnerable to electrostatic discharge (ESD) during handling and operation. ESD is the transfer of electrostatic charges between bodies at different potentials caused by direct contact or induced by an electrostatic field. If a solid-state component that is charged is then suddenly grounded, the charge will dissipate to ground. But in the process, the component will be damaged due to excessive heat from breakdown of the dielectric material within the component. Care must be taken to discharge any static electricity from the person handling the component in the workstation before touching sensitive semiconductor devices. Semiconductor materials, such as silicon and germanium, exhibit unique properties whereby the conductivity of these materials can be varied in over wide ranges by subtle changes in temperature, light intensity, and impurity content. Semiconductors are manufactured both as single discrete devices, such as diodes and transistors, and as fully integrated circuits, which can consist of millions or billions of discrete components manufactured and interconnected on a single semiconductor substrate or wafer. Their long life, reliability, and resilience in harsh environments make them ideal for use in avionics. The key to the function of solid-state devices is in the electrical behavior of semiconductors. To understand semiconductors, the following sections will review what makes a material an insulator or a conductor, followed by an explanation for how materials of limited conductivity are constructed and some of their many uses. Semiconductor materials. In periodic table, a tabular arrangement of the chemical elements, organized on the basis of their atomic number of protons in the nucleus, electron configurations, and recurring chemical properties. Elements are presented in order of increasing atomic number, which is typically listed with the chemical symbol in each box. Elemental semiconductors, known as metalloids on the periodic table, are made from a group of materials having electrical conductivities that lie between metal conductors and non-metal insulators. These group IV elements, such as carbon C silicon, Si germanium Ga, are known as elemental or single element semiconductors. Silicon is by far the most widely used material in semiconductor devices. Its combination of low raw material cost, relatively simple processing, and useful temperature range make it ideal for use among many applications. Germanium was widely used early on. However, its thermal sensitivity makes it less useful than silicon. Germanium is often combined with silicon to make very high-speed silicon germanium SiGa devices. In addition, silicon is often combined with carbon to form silicon carbide SiC devices for high power and high temperature applications. Compound semiconductors do not appear in nature, but are synthesized using two or more elements from groups 2 through Y of the periodic table. Compound semiconductors that can be synthesized using elements from third and fifth group of the periodic table include gallium arsenide, GaAs, gallium phosphide, GaP, gallium nitride, gallium aluminum arsenide, GaLas, indium phosphorus, INP, and indium antimony, INSB. The color of light that emits from a light-emitting diode depends on which of these compounds are used. Compound semiconductors that are synthesized using elements from second and sixth group include cadmium selenium, CDSE, cadmium tellurium, CDTE, cadmium mercury tellurium, CDHGTE, and zinc sulfur ZNS. Light detectors, such as photocells, are typically made from INSB or CDSE compounds. Any combination of elements, such as zinc, cadmium, boron, aluminum, gallium, indium, carbon, silicon, germanium, tin, phosphorus, arsenic, antimony, sulfur, selenium, and tellurium, can be formed into compound semiconductors with various properties. Electron behaviors in valence shells. An atom of any material has a characteristic number of electrons orbiting the nucleus of the atom. The arrangement of the electrons occurs in somewhat orderly orbits called rings or shells. The closest shell to the nucleus can only contain 2 electrons. If the atom has more than 2 electrons, they are found in the next orbital shell away from the nucleus. This second shell can only hold 8 electrons. If the atom has more than 10 electrons, 2 plus 8, they orbit in a third shell farther out from the nucleus. This third shell is filled with 8 electrons and then a fourth shell starts to fill if the element still has more electrons. However, when the fourth shell contains 8 electrons, the number of electrons in the third shell begins to increase again until a maximum of 18 is reached. The outermost orbital shell of any atom's electrons is called the valence shell. The number of electrons in the valence shell determines the chemical properties of the material. When the valence shell has the maximum number of electrons, it is complete and the electrons tend to be bound strongly to the nucleus. Materials with this characteristic are chemically stable. It takes a large amount of force to move the electrons in this situation from one atom valence shell to that of another. Since the movement of electrons is called electric current, substances with complete valence shells are known as good insulators because they resist the flow of electrons, that is, electricity. Most insulators are compounds of 2 or more elements that share electrons to fill their valence shells. In atoms with an incomplete valence shell, that is, those without the maximum number of electrons in their valence shell, the electrons are bound less strongly to the nucleus. The material is chemically disposed to combine with other materials or other identical atoms to fill in the unstable valence configuration and bring the number of electrons in the valence shell to maximum. 2 or more substances may share the electrons in their valence shells and form covalent bond. A covalent bond is the method by which atoms complete their valence shells by sharing valence electrons with other atoms. Electrons in incomplete valence shells may also move freely from valence shell to valence shell of different atoms or compounds. In this case, these are known as free electrons. As stated, the movement of electrons is known as electric current or current flow. When electrons move freely from atom to atom or compound to compound, the substance is known as a conductor. Not all materials are pure elements. That is, substances made up of one kind of atom. Compounds occur when 2 or more different types of atoms combine. They create a new substance with different characteristics than any of the component elements. When compounds form, valence shells and their maximum number of electrons remain the rule of physics. The new compound molecule may either share electrons to fill the valence shell or free electrons may exist to make it a good conductor. Silicon is an atomic element that contains 4 electrons in its valence shell. It tends to combine readily with itself and form a lattice of silicon atoms in which adjacent atoms share electrons to fill out the valence shell of each to the maximum of 8 electrons. The periodic arrangement of atoms in a crystal is called a lattice. This unique symmetric alignment of silicon atoms results in a crystalline structure. Once bound together, the valence shells of each silicon atom are complete. In this state, movement of electrons does not occur easily. There are no free electrons to move to another atom and no space in the valence shells to accept a free electron. Therefore, silicon in this form is somewhat of an insulator. Thanks for watching this video.
दोस्तों, फिर मिलेंगे अगले वीडियो में। कृपया इस चैनल को सब्सक्राइब जरूर करें। नमस्कार दोस्तों।